its name, Mergesort. Yeah, so this is another interesting sorting algorithm. C.1, Introduction to Mergesort. First, let me explain the motivation for this sorting algorithm, because this is our, so let's look at what sorting algorithms we have learned at this point. Selection sort, bubble sort, insertion sort. Now, number 4, merge sort. Yeah. All right. So why? What's the reason we want to develop another sorting algorithm? Yeah. So here, let me explain. Yeah. Problem number 13, merge two sorted arrays. Yeah. Here we consider a special operation, merge two sorted arrays. Why we consider this special operation? Yeah, I give you the reason. Yeah. Here, let me describe a special problem we need to solve. Yeah. You can imagine, some real-world situation, we may have chance to solve this kind of problem. Yeah. Given two ordered arrays, we already know each one is ordered, two ordered arrays. Yeah. Now we want to do this operation. How to merge them to get an ordered array, bigger ordered array. That ordered array contains all the elements from these two ordered arrays, and we want to use the minimum number of comparisons to solve the problem. That's our problem number 13. Yeah. It's hard. It's not hard. Yeah. First, it's not hard. Yeah. Pretty simple. Yeah. But before I go through the solution, let me give you the background, the motivation. Yeah. Give you a special situation that we need to solve this problem. Okay. All right. Why we need to consider this problem? Let's consider a special case. We want to sort a huge array. Yeah. Before we look at this question, currently, when we do the sorting, we at this point, we didn't consider the limitation of our computer, right? Yeah, I never talk about that. Currently, when we do the sorting, we didn't consider the limitation of our computer. So what do you mean the limitation of computer here? Yeah, think about, so let me explain this limitation issue. Yeah, because in the real world situation, you need to prepare for any possible cases, right? Yeah, whatever it happens, you need to find a solution. Yeah, so here we need to consider some computer limitations. What kind of computer limitations? Yeah, let me describe it here. We know computer, so here I use the space here. In the computer, all right, we have memory, main memory, and hard drive, right? Hard drive, okay, yeah. The data originally stored in hard drive. So our array, yeah, that's our data originally stored in hard drive. But in order to do processing, the data needs to be loaded in main memory for processing, right? So loaded into the main memory to do processing. Because if the data stays in the hard drive, not loaded into memory, you cannot do any processing, okay? You cannot do any manipulation. Yeah, so you have to load it into the main memory. But now the question, we know the main memory much smaller than hard drive. Yeah, main memory, we know usually several gigabytes. Okay, yeah. Hard drive could be as large as the terabytes, right? Let's imagine, okay? Or at least hundreds of times, okay? Yeah. For simplicity, let's just assume 1 TB, okay? 1 TB, that's the size of our hard drive, but our main memory is several gigabytes, okay? Yeah. So then there is a possibility if our data size is too large, we cannot load it into the main memory. We cannot load all our data into the main memory at once. Think about that. When that happens, how do you do the sorting? So that's the background behind this huge array. How huge it is. The size of the data is much larger than the size of the main memory. That huge. Think about that. Oh, we know it's rare, right? You can argue it is rare, yeah. But when that extreme situation happens, you need to solve the problem, right? Yeah. So here, we need to solve the problem. So how to do it? Let's assume this is the size of a huge array that cannot be loaded into the main memory at once. Then we use divide and conquer. The topic of this module, divide and conquer. We can divide it into several smaller pieces, and each piece can be loaded into the main memory. How about that? Okay, yeah. So we divide it into several subarrays and make sure each subarray can be loaded into the main memory at once. Yeah, so that idea, okay? Then we can apply some sorting algorithm to sort each subarray. How about that? Yeah. After we load each subarray, then we just run our usual sorting algorithm. We can get it sorted, okay? So you can imagine each subarray is sorted in order, okay? Each sorted in order. After that, our goal is to make the whole array sorted. Do you think the next step we need to do, can you relate it to the merge step I just described it above, right? Because if we consider two subarrays, each one already sorted. So the next thing we need to do, merge these two ordered arrays. That's the problem number 13 we need to solve. Okay. If we have that solution, we can apply that merge operation on every two subarrays, two ordered subarrays. So we can merge to get one bigger subarray, okay? And so on. Yeah. Eventually, yeah, we get the whole array sorted. Yeah. So that's the reason, motivation. Yeah. So we may need to apply this merge operation. Yeah. All right. So next, because if you can split, divide, and conquer, you can take advantage of parallel computing. Another reason we may need to split a big array, because right now the parallel computing, multiprocessors, very common, right? Think about multiprocessors, very common. Multi-core, okay, think about 128 core processor. Yeah, think about that. Yeah. So in order to take advantage of the parallel computing, so we can split into subarrays and make those parallel processors to do the sorting. Yeah. So after that, then we do the merge operations. Yeah. So we can, in that way, we can do sorting faster. Okay. So another reason we may need this merge operation. Okay. Yeah. Next, let us find a solution. Yeah. This merge operation, although it's not hard, yeah, but we need to find its solution. Yeah. All right. How to merge two sorted arrays? Yeah. Given two arrays that are already sorted, how to get a new sorted array that contains all the elements. Yeah. Okay. All right. Here, when we do the merge, we should not run any sorting algorithm for the data we have another time, because that won't, in that way, we do not take advantage of the structured data. We already, because the structure of the current data is very good, we should use that structure. We should take advantage of that structure so that we can use much fewer number of comparisons. If you do not take advantage of that structure, nice structure, you just apply a sorting algorithm on the data combined from both subarrays, then your performance could be very slow. Okay, yeah. Here, the main thing, we should not start over again, just run the sorting algorithm in some blind way, yeah, because you do not consider any special structure you already have. Just run some sorting algorithm in a blind way. Then you won't get good performance. Yeah. Here, we want to do it in a smart way. The smart way, the nice structure, each one already ordered, that structure can help us reduce large number of comparisons. So that's what we are going to do here. Yeah. All right. Do not use any sort that does not, yeah. So that's what I said. Yeah. So you need to really explore the special structure in these two subarrays. Yeah. All right. But here, let us consider, based on our experience, we have learned three sorting algorithms: selection sort, bubble sort, and insertion sort. Yeah. And we want to borrow some experience from these three sorting algorithms. Yeah. But we need to pick the right one. So which one can provide us some helpful experience. Yeah. So that's something we need. Yeah. But when we do our selection, we want to see which one of the three gives us the property that can take advantage of the ordered information. That's something we need. So which one can take advantage of ordered information of the data? That's the one we need to borrow some experience, borrow its, solution, idea of the solution. Yeah. First, let's look at a selection sort. Let's recall for the selection sort, when the array is already ordered, when the array is already ordered, if we apply selection sort, can we get a better efficiency? If the array, we know it's already ordered, but we just assume we do not know it. We apply selection sort on this ordered array. Do you think we will get a better efficiency? The answer is no. Even if it is ordered for the selection sort, you get a big, let me right here, big theta of n squared. Okay, even if it is ordered, because I assume you know the details of the selection sort, because every time we find the minimum, okay, the first time finding the minimum, we get n minus 1 comparison, second time n minus 2 comparison, and so on. Okay, even it is already sorted, you still, because you cannot see it, right? You cannot. In computer, when you run computer algorithms, computer does not have eyes, so computer cannot see it is sorted. Okay, it still use the selection sort step by step from beginning to end, so the performance still, it will be big theta of n squared. So for the selection sort, it does not help. Okay, it does not take advantage of the order information. So we should not consider selection sort. All right, bubble sort. Bubble sort, if the array is already ordered, still big theta of n squared. Doesn't help. The same reason as that of the selection sort. It doesn't help. But insertion sort, we learned last time, insertion sort, then it's different. Insertion sort, if the array is already ordered, then the efficiency is big theta of n. It is greatly reduced. It is reduced from n squared to big theta of n. That's a big improvement. That means the solution of the insertion sort, it helps us a lot. So we should borrow the solution from insertion sort, or the idea of the solution from the insertion sort to solve our current merge to ordered array problem. So, all right. So when we work on the solution, we consider that insertion step. Because the main step of the insertion sort is the insertion step. So the insertion step should shed some light to our new solution. Shed some light. Okay, all right. We know insertion sort has some good property. This is the good property. Good for almost ordered array. Yeah. But here we have two ordered array. If we put them together, we can treat as a special case for the almost ordered array. Yeah. Although not exact what we mean last time, yeah, but sort of. Yeah, let's say this, sort of. Yeah. Not exactly what we describe it. So what we described last time, almost sorted. But sort of. Yeah. All right. Yeah. Next, let's look at the solution part. Yeah. All right. This time we take a different view on insertion step. We want to borrow the experience of the insertion step as our starting point. When we start, let's look at the insertion step first. We have to do modification. Yeah. So let's recall that insertion step. Yeah. Why take a different view? Because we can get a new idea. When you take a different view, then you may find some new insight. Yeah. And a new solution could come from that new insight. Yeah. All right. Yeah. So let's look at the insertion step. This is a typical insertion step. Yeah. The left subarray already ordered. It is sorted. Yeah. And we need to insert a new element V into an already ordered array. That's the typical insertion step. Yeah. Yeah. So the detail, right? You need to compare. Yeah. So we do comparison with the last one. If it's smaller, another comparison until we find the right position. That's a typical insertion step. Okay, yeah. All right. But can we treat this V element as one element array, a special case? Yes, one element array, right? We can treat it as an array. So this subarray only has one element. Yeah, special case. Yeah. But if you look at it in that way, then we have two subarrays. Left subarray ordered, right subarray very small, but it is still ordered. Can you treat the insertion step as a special case of the merge step, merging two ordered arrays, right? Yeah. So we can borrow that old experience because they're closely related in this way. Yeah. Merge two ordered arrays. Yeah. All right. Yeah. It's sorted. Yeah. Although the size, not quite balanced. One is very small, one is relatively big, not quite balanced. Yeah. It's okay. Yeah. But we can extend it, right? Yeah. When we start this single element subarray to extremo, but we can extend it to a normal ordered array, right? Yeah. Okay. New interpretation. Yeah. Two sorted arrays are combined to get a new sorted array. And that insertion step is pretty much gives us the basic way to merge two sorted arrays. Yeah. But we need to do some modification. Yeah. All right. Yeah. Okay. So the new view, merge two sorted arrays for a new sorted array. Yeah. Every time we find the right position for one element, or every time we put one element in place. Yeah, remember the terminology. Yeah, in place. Yeah, put one element in place. Yeah. All right. Yeah. Okay. Yeah. Data size. The first array has k elements, but the second array has one element. That's for the insertion step. All right. Not balanced. Yeah. Because if the data is not balanced, based on our experience, usually that property would result in poor worst case. Yeah. Poor worst case. If the data is distributed in some unbalanced way, that usually result in worst case. That's something we want to avoid. So when we have a chance to distribute data, we want to distribute data evenly, as even as possible, in order to avoid worst or poor worst case. So that's some experience, the experience we have, you know, when we work on real world problems. Yeah. All right. To improve performance for the worst case, we use some balancing principle. Yeah. So yeah. Yeah, because this is some principle, right? It's not a theorem, so we cannot prove it. Yeah, based on our experience, we just realize when the data is distributed in a balanced way, we can get a better solution. All right. Yeah. Try to make two subarrays of equal size. Yeah. When you have a chance, when you have the freedom to do it, then you should do it in a balanced way. If you do not have the freedom, then you just take whatever you have. But here, it looks like we have the freedom to choose how to split our data. So we will take advantage of this freedom to split the given data as even as possible. Yeah. So the next round, next page, we will do divide and conquer, but when we do that divide step, we try to split evenly, split the data evenly. Yeah. All right. C.2, merge operation. Now we look at the detail of the merge operation. Yeah. All right. How to achieve balanced subarrays. Yeah. The divide step. First, we need to split the given data. We have freedom. Nobody told us which way to split, right? Yeah, we have freedom to split the data as we like, right? Yeah, here we will take advantage of that. Okay, idea: whenever we merge two subarrays, we make them of equal size. Yeah. Sometimes it's not possible of equal size, but as even as possible. Yeah, because sometimes you have odd number of elements, right? You cannot split evenly, right? But we will split. One subarray has just one more element than the other one. Yeah, that's the best we can do. Okay, yeah. So here, so we will do it that way. I draw this diagram to show you the even split way for divide and conquer step. All right. This whole line segment represents the original array. Yeah, this many elements. Yeah, we do divide and conquer. The first time when we we make split as even as possible. So, you know, yeah. At the most, one difference, right? Yeah, could be. So the difference of the sizes of the two subarrays could be 0 or 1. Yeah. That's the, you know, as even as possible. Yeah. Difference of the sizes, 0 or 1. Okay. Even 0. Odd, difference of the two sizes, 1. Yeah. All right. So the first split, right in the middle. Okay. Yeah. One subarray could be one more than the other. Yeah, that's fine. So we just try the best we can do. Okay. Yeah. Divide, then conquer. All right. Conquer. But conquer means we make each subarray sorted. But when we do the sorting, we need to apply divide and conquer another round. Okay, yeah. So another split in each subarray as even as possible, like this. Okay, yeah. After 2 rounds of split, you can see, you know, each subarray has approximately quarter size of the original array. All right, yeah. But still, we need to conquer each one by divide and conquer. So another round split. All right. So you can see each subarray, its size becomes smaller and smaller. Yeah. But we need to stop somewhere, right? We cannot split forever. Yeah. Stop splitting when each file, each subarray contains one element. Yeah. That's the end. One element, you cannot split anymore, right? You have to stop it. One element. And one element, it's already sorted. It's ordered. One element, when we treat it as a special subarray, it is already ordered. All right, so then after that many splitting operations, we need to reverse the process, right? We need to merge all these subarrays and eventually to get the whole array sorted. Yeah. Next, let's look at the merge step. Yeah. When we do merge, we merge 2 adjacent subarrays. 2 adjacent ordered subarrays. Yeah, we assume they are ordered. Okay, we merge 2 adjacent ordered subarrays. Yeah, to get larger ordered subarrays. Okay, that's the first round. Next round, merge again 2 adjacent ordered subarrays to get even larger ordered subarrays. Yeah. Another round. Yeah. So round. Yeah. Another round. And finally, at the end, we merge 2 ordered subarray to get a whole array sorted. That's the idea of this merge sort. Okay. Yeah. So using this diagram, you see the high-level idea, understanding of this new sorting algorithm. Okay, yeah. So you can see if we can find that merge solution, then using this divide and conquer way, we can get a whole array sorted. Yeah. But we need to figure out the details of that merge step. Yeah. So it's missing. Right now, we need to fix that detail part. Yeah. All right. Yeah. hope it can avoid poor worst case performance. Yes, because we do the even splitting, right? So we try our best to avoid unbalanced data distribution. Yeah, and we hope to avoid poor worst case performance. Yeah. Later you will see, yes, yeah, in this way, the merge sort definitely avoids poor worst case. Yeah. So later I will explain that part. Yeah. All right. Now, the critical missing piece, main step, merge step. If we get this merge step, then we're done. Yeah. So then the whole merge sort is there. Okay. Yeah. So, but that part, that piece, that part is critical for this algorithm. Yeah. So let's work on it. Okay. Yeah. Here I use this diagram to show you how to merge two subarrays. Here, these two subarrays, each one has k elements. Yeah. A subarray and a B subarray. Yeah. We assume they are ordered. All right, so let's work on the comparison operations. Yeah. So how to work? Yeah. All right, yeah. The first time we compare A0 and B0, two smallest elements, A0 and B0. Okay, that's the first time. All right. And the smaller one, we use this notation, min 0. That is the minimum of A0 and B. So the minimum of the two elements, we know that should be the minimum of all the elements in these two subarrays, right? Yeah. That's the absolute minimum of all the elements we have here. So that element should be the first one in the final ordered array. Then the maximum, max 0, assume that is the max of the A0 and the B0, but that one, we do not know its position for the max 0. We know the min 0, we know the position of the min 0, that's the first one in the final ordered array, but we do not know the position of the max 0. Yeah. So we will find its position later. Okay, all right. So let us arrange sufficient empty locations for the final ordered array. So these empty boxes, so that's the locations for all the elements in our destination ordered array. Yeah. After the first comparison, the min 0, that one, we know it should be placed as the first element in our destination array. Min 0, yeah. The minimum of all the elements. By one comparison, we find the minimum of all the elements. So we put it in place. Yeah. The first position in our destination array, that's the right place for this element. All right, so what is the next one? Next one, the survival, yeah, you know, whatever you like to call max 0. Yeah, we do not know its position, so we need to do another comparison. Yeah, max 0. Yeah, here we consider that, let's say B0 is that max 0. Yeah. Assume B0 is that max 0. Yeah. The next round comparison, next time comparison, we should compare A1 and a B0. Yeah. A1 and a B0. Which one is smaller? The smaller one, and we use the mean one, the smaller one of A1 and a B0. Mean one should be the second element in our destination subarray, right? Destination array. Yeah. So after our second comparison, mean one is in place, and so on. Yeah. So you can see, yeah. Yeah. But it could be the mean one could be B0, right? Whatever it is, if the mean one is B0, then max one will be A1. So the next time we need to compare A1 and a B1 and so on. Yeah. So then we do this until we reach the end of the array. Yeah. Because when we have last element left, we just put it in the last position. No comparison needed. No comparison needed. Yeah, because only one element left. We just put it in place immediately. Okay. Yeah. After that, we get whole array sorted. Yeah. So let's look at how many comparisons do we need to merge these two ordered subarrays. Each comparison will place one element in place. But the last one, we do not need to do any comparison. Yeah. So you can see, yeah, for the worst case, 2k minus 1 comparison is needed. We need 2k minus 1 comparison. We have total 2k elements, but last one, we do not need any comparison. So the total number of comparison we need, 2k minus 1. Well, that's the worst case, not the best case. Okay, that's the worst case. The maximum number of comparisons we need to get two subarrays merged. Okay, yeah, yeah, all right. But here, let's consider worst case for the general merge step. Yeah, so what do you mean general merge step? The sizes of these two subarrays may not be equal. That's the general case. The size of the first subarray, n elements. The size of the second subarray, n elements. Yeah, they're not necessarily equal. Yeah, but we can still apply the same procedure as before, right? Yeah. So each time after one comparison, we just put one element in place. Except the last one. Last one, we do not need to do any comparison. Yeah. Now you can see for the worst case, how many comparisons we need for the worst case. You can see the answer is the total number of elements minus 1. N plus n minus 1. To merge any two ordered subarrays, it's worst case n plus n minus 1. Yeah, so that's the answer. Okay, yeah, all right. But how about the best case, right? Yeah. We just did the worst case, but how about the best case? Yeah. Think about the best case. We do not need that many comparisons. Yeah. So think about what is the minimum number of comparisons we need for the best case. So that's also interesting. Yeah. Yeah. you need to imagine some scenario on the what special situation you can make the total number of comparisons to be the minimum you can have. Yeah. Think about some extremal case. Yeah. One extremal case you can imagine is, think about if B0 is greater than all the elements in A subarray. That's possible, right? B array is greater than any element in A subarray, or B0 is greater than the maximum, the last element in A subarray. If that happens, you only need to do comparison B0 with all the elements in A subarray. After you beat all of them, then the remaining elements B1 through Bn minus 1, you do not need to do any comparison, right? Yeah, because B0 already beats all elements in A subarray. After that, after you put all elements in A subarray in place, then you put a B0 in place. For the remaining B1 through Bn minus 1, you do not need to do any comparison. You just put them right in place in the destination array immediately. Okay? Yeah. So here, the strategy, try to exhaust one of the two subarrays as early as possible. How to exhaust? Yeah. You just imagine the minimum of one subarray beats all the elements of the other subarray. When that happens, you exhaust all the elements in that subarray as early as possible. When that happens, you may get a minimum number of comparisons. Yeah. All right. So then the conclusion, exhaust, because you have two cases. You either exhaust the A subarray or exhaust the B subarray, right? Yeah, two possibilities. Yeah. So which one is better? Exhaust the shorter array is better. Yeah. Because you can terminate earlier, right? Your algorithm can terminate earlier if you exhaust shorter subarray. Yeah. All right. So the conclusion for the best case efficiency, so that is the minimum of n and n. Minimum. This many comparisons for the best case, the general best case. Yeah. Okay. All right. Yeah. Because after this discussion, so we understand the merge step well. So that's the standard merge step in this way. All right. So now we complete the merge step. After we complete the merge step, we complete the merge sort. So go back to our previous a few slides, that divide and conquer diagram, with that divide and conquer, even split with, this kind of merge step, we can get that merge sort. All right. But here I may like to make some comments. But because some student ask me the question like, because based on the standard merge sort, we compare A0 and a B0 first. That's the standard merge sort. But some students may ask me why we do not compare B0 and A minus 1 first. B0 and with the last element of A element. Because if B0 can beat an-1, then we only need one comparison. Yeah, so that's one student asked me this question last semester. Because for that special data, this way definitely you get the best solution. But in the general case, you may get a worse. You may get a poor performance, right? Think about it. So if an-1 greater than b0, you may go to backward, right? an-2 next, and so on. You may go backward like that, right? So that means in the general case, you may not get better performance. You only get better performance for a very, very special situation, but not the general situation. Okay? So that may not be a good idea. All right. Okay. Then C.3, efficiency analysis for merge sort. So this time we need to see for a general N, the data size general N, what kind of efficiency function do we have? All right. In order to find that answer, so we need to do some math computation here. All right. Derive recurrence relation. The first step, we need to estimate the worst case efficiency. So let's look at the worst case efficiency first. Remember something we need to do, I mentioned before, we do even split on our data. Its goal is to avoid poor worst case. Here, let's look at how poor is its worst case. Is it pretty good? Is it much better than our old sorting algorithm for the worst case? So we want to see that answer. Estimate the worst case efficiency. So let's look at this diagram. We split evenly to get two almost of equal size. For simplicity, we just assume we split right in the middle. Okay? But after that even split, we have two subproblems like this. Okay? Each one approximately half of the data size, original data size. Let's assume the efficiency function is capital T of n for the original problem. After that even split, we need to conquer two subproblems. And for each subproblem, the number of comparisons we need, T of n over 2. That's the number of comparisons for each subarray. All right. But we need to do merge operation, right? After we sort these two subarrays, we need to do that by conquering step. After that, we need to merge these two ordered subarrays. So what is the cost to merge these two subarrays? We just derived in the previous slide. The total number of elements minus 1. That's the combined step. That's the number of operations. Actually, it's n minus 1, but for simplicity, we can use n. Total number of elements, n. So although we need n minus 1 operation, but this minus 1 is too small, we can drop this n minus, or drop this minus 1. All right? So we write the recurrence relation, two base cases. T of 1 equals 0. No comparison needed if you have one element, right? Yeah. T of 2 equals 1. When you have two elements, you only need to do one comparison to get it sorted. Yeah. Then for the general case, T of n equals 2 times T of n over 2. Yeah. You conquer, you sort two individual subproblems. But you need a last merge step. Last merge step, we know we only need n minus 1 comparisons for the worst case. But that minus 1 is too little, so we just drop them minus 1. So we just put this n here for simplicity. Okay. So the next thing is we need to solve this recurrence relation to find the answer. Yeah. But here, how to solve it? Yeah, we consider simpler case. Yeah. So what's the simpler case? When n is power of 2. That is the easiest case because you can always do even split. And when n equals a power of 2, you can do the even split all the way down to the single element bottom case. Yeah. So that's the easiest case we can think of for the general case, general situation. Yeah. All right. So when n equals 2 to the k power, yeah, what is the formula for this t function? We want to find it. Yeah. So let's, replace n by 2 to the k. Yeah. So we get a new equation like this one. Yeah. The next step, we need to do transformation. Yeah. In order to solve this equation, we need to do transformation. Yeah. So this step is important. If you do the right transformation, then you can see the structure clearly. Yeah. So let me show you how to do it. Division method. We do division both sides of some special number. So which number? 2 to the kth power. That power. Yeah. So we do, after we do that division and some simplification, we get this new form of equation. Then you examine this new form of the equivalent equation. Can you see something special here? Special property we can take advantage of for this one. Yeah. You can see the left-hand side, this fractional operation, ratio operation, and the right-hand side, this one, they have similar structure, right? They have similar structure. Yeah. The only difference is k and the k minus 1. That is different. Other than that, structure-wise, they are the same. Yeah. So we can take advantage of this similar structure. Yeah. So how to take advantage of the similar structure? Yeah. We define a new function, yeah, to represent this special structure. Yeah. So let us use a new function g of k to represent t of 2 to the kth over 2 to the kth. Yeah. After we define this new function, we can simplify that, we can simplify this form, this representation in a much simpler way. Yeah, after we define this g function, yeah, then we do substitution. And after the substitution, we get this equation. G of k equals g of k minus 1, parenthesis, plus 1. How simple it is. We greatly simplify that old form, right? Yeah. So you can see after we introduce a new function notation, capital G of k, we can make our new equation much simpler. Okay, yeah. And to solve this simpler recurrence relation, yeah, that's very easy. Yeah, yeah. Here, if you plug in g of 1, k equals 1, yeah, it is 1/2. Yeah. So that's the base case for our G version of recurrence relation. Yeah. Now let's solve this G version of recurrence relation. Okay, yeah. Let's just apply this recurrence relation another time. G of k minus 2 plus 2. Yeah, because we replace this G of k minus 1 by G of k minus 2 plus 1. Okay, plus 1. That one and this one combined, so we get 2. Okay, and so on. Yeah, we can do, you know, this kind of recurrence function call again and again. And what is the last one? Think about. Can you keep track of the last equation? How? Because this dot dot dot, we may get lost, right? If we use this dot dot dot, how do we keep track of the right version of this equation? Yeah, here, use the invariant idea. Invariant. Do you remember invariant idea? Did I talk about that invariant idea before? Yeah, no, yeah, probably not. Yeah, I mentioned once. Yeah, did I mention? Yeah, probably not. Yeah, here, consider some invariance. So what's that invariance? Yeah, look at the sum of k minus 1 and 1. That is k, right? The sum of k minus 1 and 1, that's k. The sum of k minus 2 and 2, also k. That k never change when we apply this recurrence function call. Never change. That number we call it invariance. Yeah. We use that invariant, the size number plus that constant. The sum of these two numbers, that's invariant. Never change. We use this invariant to keep track of the correct version of each step until we reach the bottom one. Yeah, this invariant equals 1 invariant. Yeah, until we reach the base case g of 1, the last g of 1, and we know after we apply that invariant, this place should be k minus 1. Because the sum should be k. 1 plus k minus 1, the sum should be k. So this idea helps us to keep track of all the middle equations. Keep track of them. All right. Then the final solution. Yeah. Before I finish today, let me give you the final solution. Because g of 1 equals 1/2, so let's plug in. So we get k minus 1/2. Yeah. But we need to go back to the original n number. So not in terms of k, we should get the answer in terms of n. So let's go back. Yeah. All right. So go back, we know this, it equals k minus 1/2, but we need to go back to t. Yeah. T of 2 to the k equals big parenthesis k minus 1/2 times 2 to the k. Yeah. But we need to go back to the original n. Yeah. All right. And we replace 2 to the k by n, and k log base 2 of n. Yeah. So let's do that last substitution. So we get t of n approximately equal to n times log n. Approximately, yeah, because we dropped that 1/2. Okay. After we drop that 1/2, negative 1/2, yeah, so it's an approximate, good approximation. Yeah, we didn't drop too much, only 1/2 inside the parenthesis, so we get t of n approximately equal to n times log base 2 of n. Yeah, but this comes from the special assumption that n equals 2 to the k. That's a special assumption. All right, yeah. So we get this n log n formula expression. Yeah. All right, yeah. Let me stop right here. For further discussion, I may have one or two slides. We will complete it next time.